Hello everyone. Today we are going to make a presentation on our 990p main project, which is the design and analysis of piezoelectric layered energy harvester model on wind turbine for turbine control. We had the pleasure of being supervised by Dr. Mohsen Jamal, and this project has been conducted by Mr. VENKATA and myself. In this project, we are mainly going to explain what's the objective of the project, what is piezoelectricity, different types of piezoelectric devices, different types of piezoelectric energy harvester models, wind turbines and its control mechanisms, like the pitch control of a wind turbine or the yaw control, and the different types of mechanisms which allow the control of the pitch or the movement of the wind turbines, along with what is a piezoelectric bender, how a piezoelectric bender operates, and modeling of wind blades with piezoelectric bender attached to it, which would further improve with the stability of the wind turbine, along with the console simulation of the wind turbines, which includes the finite element analysis of the wind turbine, and a simulation of this model has been done in MATLAB software by first making the wind turbine blades in SolidWorks and then making a mesh analysis of this same wind turbine blade with piezoelectric layered, and then making a compound simulation by doing an FEA analysis, that is finite element analysis, and then further making a simulation model of the project. And we have found very conclusive results and have made a conclusion based on those results. Thank you. The objective of this project is to design and analyze an energy harvester model based on piezoelectric bender. The main principle that we are employing is to create or design a piezoelectric layer, that is an energy harvester layer, on the surface of the wind turbine blades, which would further improve its rigidity and surface strength of the wind turbine blade, and enhance and reduce the unwanted load on the wind turbine blades that would increase the energy efficiency of the wind turbine. We are planning to simulate such a model using the piezoelectric material, which works on the process of piezoelectric bender, that is using the bending principle of the piezoelectric material to generate electrical energy, and using this electrical energy to power the control mechanisms of wind turbines. To be specific, that is the pitch control mechanism of the wind turbine that we are planning to design and simulate using. We are planning to energize using the energy obtained from the energy harvester model, um, which is then used to control the pitch control mechanism, to power the pitch control mechanism of the wind turbine. In the previous project, that is in 990A, we designed a hybrid wind micro hydro energy system using MATLAB, and we did the financial analysis of the same using HomoPro software. This is the further continuation of the project where we design and analyze energy harvester model for the wind turbine blades to generate energy to control the pitch control mechanism of the wind turbine. At first, let us define what piezoelectricity is. Piezoelectricity is a phenomenon by which an electrical field or an electrical energy is generated when a pressure is applied on a piezoelectrical object. Pressure or mechanical force can be both used to produce electricity. This phenomenon is called as piezoelectric effect. Here, the kinetic energy in shock form is converted into electrical energy. Here in figure 1, we can see a piezoelectric energy harvester schematic diagram. Here we can see when pressure is applied across a PZT, that is a piezoelectric thin film layer, and electrical energy is produced. We can see the electrical equivalent circuit of the piezoelectric effect that is happening. It consisting of the energy produced, the capacitor, and the resistor unit, which is then passed into a rectifier, which converts an AC electricity into DC form, that's a direct current, and direct buck boost or buck converter is used, and then the amount of energy that is produced has been passed on to the load. The piezoelectric materials can be classified into two types, the piezoceramics and the piezopolymers. The difference between the piezoceramics and the piezopolymers are that the piezoceramics have a large electromechanical coupling constant, which means they produce higher amount of energy with less coupling, and they have a higher energy conversion rate. They are too brittle to use in general shape energy transducers. The example of one of the piezoceramics would be lead zirconate titanate, that is PZT5H and PZT8. The piezopolymers have smaller electromechanical coupling constants compared to that of piezoceramics, but they are very flexible in nature. And the example of a piezoceramic polymer or a piezopolymer would be a polyvinylidene fluoride. The piezoelectric energy harvester model, based on the vibrational energy harvesting piezoceramics, can be classified into four types: the cantilever type, symbol type, stack type, and the shell type. Here, the cantilever type and symbol type are the most commonly used types of energy harvesting piezoceramics. In the case of cantilever type of piezoceramic, we can see that the load or the force is applied tangentially to the surface of the piezoelectric material or in a perpendicular nature, thus creating a force which would bend the fabric of the piezoelectric material, which is supported by an elastic piece in order for the piezoelectric material, like a piezoceramic, for not to break. Such type of mechanisms are followed, or such type of principle is followed in cantilever type of energy harvesting piezoceramic. Whereas in symbol type of piezoceramic, the force or the mechanical load is applied longitudinally or through the surface of the piezoelectric piece, which creates a force that is in parallel to the surface of the piezoelectric material. In the symbol type of piezoelectric energy harvester model is commonly used for the processes which involve the production of micro energy or where micro electrical energy is required. Wind turbine control mechanisms. Wind turbine control is one of the most important aspects in the operation of wind turbines, as there are unwanted loads caused by the wind at the input shaft, which are like sudden changes in the wind direction, uneven loading of blades, wind turbulence, and accumulation of dust on the blades, which results in uneven balance of the wind turbine blades, thereby reducing its efficiency. To overcome such disturbances, we need to design a control system or control mechanisms which would allow us to get rid of all the negative factors that affect the wind turbine. Such control mechanisms include the torque control, pitch control system, and the yaw control system, to name few from many in case of wind turbines. In the control mechanisms or the control system that I explained above, some of the most commonly used control systems in a wind turbine are the torque control system, yaw control system, and the pinch control system of a wind turbine. Let's consider the torque control system of a wind turbine. The generator torque of the wind turbine is controlled as the generator torque controls its the wind turbine rotor speed in order to obtain maximum power production, that is, variable speed operation of the wind turbine. The controller must adjust the controller generator torque for accelerating or decelerating the turbine to operate at optimal condition. In the case of yaw control, angle of attack affected by changing the yaw angle of the wind turbine is managed. That is, the yaw angle of the wind turbine is changed in order to change the angle of attack to control the amount of air that is passing through the amount of air or wind that is passing through the wind turbine. Different aerodynamic behavioral patterns can be obtained by this control of the yaw angle of the wind turbine. When there's a sudden change in the wind direction, the yaw angle can be controlled to bring the wind speed to the required speed of the wind turbine in order to obtain maximum efficiency from the wind turbine. Pitch control mechanism of a wind turbine. The mechanical power of a wind turbine is controlled by the pitch function. If the wind speed is greater than the rated wind speed, the pitching angle of the wind turbine is increased in order to reduce the wind speed to the rated value. And the vice versa condition is applied. That is, if the wind speed is less than the wind speed, the rated wind speed, the pitching angle has to be reduced in order to increase the wind speed to the rated value. So, for this operation to occur, we require a control system to control the pitching mechanism. And the energy for this control system is provided by the piezoelectric energy harvester model that we have currently simulated. Piezoelectric bender. The energy harvester consisting of a piezoelectric bender, a rectifier, and a DC to DC converter. From the figure 5, where we can see a piezoelectric bender model, the left end of the piezoelectric bender is clamped to a vibrating object, forcing the motion. The right end of the piezoelectric bender is connected to the extra mass. This model of the piezoelectric bender is obtained in the MATLAB libraries by employing the following code as shown in the description. Due to the elasticity, mass, and inertia of the piezo bender, the motion of the right end is not synchronous to the left end. The deformations produced then create a charge and a voltage across the electrical terminals of the piezo bender. That is used to utilize the power. That is used to harvest the power, which is then forwarded into the pitch control mechanism. The full wave rectifier transforms the AC power generated by the piezoelectric power into DC power with the help of diodes and capacitors that act as a filter to smooth the DC voltage. The buck converter regulates the voltage to transfer maximal power to the load, and transfer of power is unidirectional in nature.
And moving on to the modeling of the blades. So firstly, with respect to the dimensions of the blades, corresponding geometry is developed in SolidWorks software. And the geometry file is then imported into the COMSOL multiphysics software for the analysis purpose. And here we have carried out the finite element analysis, and the material properties considered are PZT5, which is the standard piezoelectric material assigned to the turbine. One important technique in the developing of numerical model for finite element analysis is meshing, and meshing is the second most important requirement in COMSOL. And meshing basically involves generating a mesh around the considered model, and because of this mesh, results can be captured with appropriate amount of accuracy. And in figure 7, we can find the mesh design of the wind turbine blade, and the next aspect is simulation of blades on COMSOL multiphysics software for finite element analysis. And figure 8 explains the same of wind turbine blade at 26.35 Hz frequency. So for the model analysis to determine eigenfrequencies of the wing, firstly the wing model will be fixed at one end, and in our case the considered model, there is a larger width towards the end of the wing. And similarly, we have also carried out finite element analysis of the blades at different frequencies. And in this case, figure 9 shows FEA at 133.16 Hz frequency, and figure 10 shows 169.64 Hz frequency. And in figure 11, we can see finite element analysis of the wind turbine blade, and there is a brief comparison of arc length versus displacement magnitude. So the eigenfrequency study was basically carried out to get the eigenfrequency values, and the plot for first three sets of eigenfrequencies is shown here in figure 11. And based on the magnitude of the frequencies, the amount of displacement produced in the wing is shown as a function of arc length of the wing.
Here in figure 12, we can see the model of a piezoelectric bender. In the right portion of the piezoelectric bender model, we see the wind turbine and the pitch control mechanism, followed with the rectified output. To the left, lower end of the model diagram, we can see the piezoelectric bender, which is used to which on given the vibrational energy, that is the kinetic energy, produces electrical energy. This electrical energy is then passed through a full wave rectifier and a buck converter to obtain a rectified proper output that is required. And this energy is stored in a battery. The output of the battery can be seen in the following figures. Then this output from the battery is powered is given to the pitch control mechanism after it passes through a universal bridge that rectifies the output further to required value. This output is then given to the pitch control system as shown in the top left of the diagram. And this output is then passed to the pitch angle control mechanism of the wind turbine, and the required energy is generated, and the wind turbine functions as efficiently as possible. The above-mentioned model with a piezoelectric bender, which helps to generate energy using the energy harvesting model, along with the rectifier and the DC to DC converter unit, which is the piezoelectric layer which is installed or which is enamored on the on the surface of the wind turbine blades to generate energy to power the pitch angle control of the wind turbine. The following are the specifications of the wind turbine blade where the piezoelectric compound has been used. The length is kept at 30 meters with a cross section of 0.58 meters, the thickness of 5.08 into 10 to minus 4 meters, and a weight about 2,300 kilograms. On simulating the above-mentioned energy harvester model with the natural frequencies of wind between 26 to 169 Hz, we found that the wind blades have different displacement and disturbance and deformity values with each eigenfrequency of the wind. An analyzer module was used to obtain the value of voltage, which is from the piezoelectric bender, which is given from the battery to power the pitch angle control mechanism to run the wind turbine. The output values of the three-phase voltage and current of a wind turbine when subjected with angle control, which is powered by an energy harvester model with the input parameters such as the wind speed, which is set at 10 meters per second, are as follows. Here in figure 7, 8 and 9, we can see the output of the simulation from the MATLAB for the energy stored in the battery from the piezoelectric energy harvester. In figure 7, the three-phase voltage output from the wind turbine with energy harvester model and the three-phase current values for the same. From the figure 7, we can obtain that the constant current that value that is obtained, the current or the ampere hour value that is obtained from the piezoelectric layer for the specified specifications were around 800 ampere hours, and the three-phase voltage and the three-phase current values obtained, which is used at the end of the wind turbine, which is obtained at the end of the wind turbine, are as follows in figure 8 and figure 9. From the results obtained from the SolidWorks COMSOL simulation as well as the MATLAB model, the following conclusions were derived. Results from the COMSOL software for generating the finite element analysis of the wind turbine allows us to come to a conclusion that the amplitude of natural frequencies of wind has an effect on the deformation and thereby the stress and load on the wind turbine blade. Results show that the power that is obtained or stored in the battery from energy harvester model in the MATLAB simulation is sufficient enough to run the pitch control mechanism of the wind turbine. It can be made certain that the piezoelectric can be used as a power control mechanism that requires less power in wind turbines. Furthermore, many studies can be conducted to expanding the scope for the utility of piezoelectric layer for the wind turbine blades as a substitute to reduce the drag and improve the stability of the wind turbine blades and make the wind turbine more efficient. We would like to thank everyone for their time and consideration for going through our project. Thank you very much, and we are open to any queries regarding the project. Thank you again.